Hello everybody. This section is about the application of plane stress. The plane stress, if we translate into 우리말, it is translated into 평면 응력. The plane stress. Here are the content of this section. So after the outline, we'd like to talk about the pressurized vessels. And then as a typical application of plane stress conditions. And then in here, from item 3 to item 5, we'd like to talk about stress trajectories found in beam problems and the principle of superpositions and the combined loads. So here, this section consists of two different parts. Part 1 is the problems in regarding the pressurized vessels, and the part 2, which basically we're going to talk about the practical problems found in beam problems. For example, the stress trajectories following the principal stresses, and then principle of superposition, and how to use the principle of superposition for the structural analysis. Alright, so first let's check two different kinds of two-dimensional simplification of actual three-dimensional stress states. As I told you several times, the stress states actually the three-dimensional problems, but in some special cases we can simplify the stress states into two-dimensional problems. The first one is the plane stress. As I told you, it is translated to 평면 응력. And the second case is plane strain. It is translated to 평면 변형률. Actually, we have plane stress condition when we deal with very thin, problems. What I mean, the one dimension, the dimension in the thickness direction is much shorter than the other two. For example, if we compare the thickness to the width and the length of the specimen, the problems, the thickness is very small. Typically, the thickness is less than about a tenth of the width or the length of the specimen. We can consider this is plane stress problem. The characteristics in the plane stress problem, the stress variation, the thickness direction is very small. This is the characteristics of plane stress problem. And then second one is the plane strain problem. In the case of plane strain problem, strain change in the thickness direction is very small. So when we have such kind of plane strain problems, let's consider pavement. In the case of pavement, so we have a cross-section pavement, but the length of the pavement is much longer than the other two. Or the thickness of the pavement and the width of the pavement, but the length of the pavement is much longer than that. So which means the strain measured and strain change in that direction is almost equal to zero. Okay, that's why we call it plane strain problem. So we do the analysis only for this cross section in these both problems, but in this cross section. Okay, sorry about it. These are two-dimensional problems, but in first case is plane stress and second case is plane strain. So make sure that the fact that in the case of plane stress problem, stress is equal to zero in the thickness direction doesn't mean that the strain change in the thickness direction is not equal to zero. The strain changes. So imagine that you apply the membrane action, that because of Poisson effect, the thickness changes. Okay, the strain in according to this coordinate system, epsilon zz is not equal to zero. Okay, and then also here is same. Epsilon, this is a plane strain problem. Epsilon zz is equal to zero. It doesn't mean that the stress in z direction is equal to zero. It doesn't mean that. Usually the stress in the thickness direction is not equal to zero. Okay, so here let's consider a realistic problem. Here we'd like to consider two different specimen. Specimen means this is 시험체. So here we have a notch, and then let's say the width of the specimen is same, and also the length of the specimen is same. But the difference is here the thickness thickness in the first specimen, thickness is much smaller than the width of the specimen. But in the case of the second one, the thickness of the specimen is much greater than the width of the specimen. So the first one is a plane stress problem. The second one is plane strain problem. So here the development of plasticity is different apparently, right? So in this case we have the development of plasticity in the ligament direction. So we have plasticity development, but in the case of second one, we have the development of plasticity in two different directions. This is what happened in the plasticity. So if you measure the resistance per unit thickness of this two-dimensional problem, it depends on the thickness. Say there exists some optimum thickness where we have the maximum resistance, but before this maximum thickness we have the plane stress condition and the plane strain condition. It depends, okay? Let's look at realistic and actual structures found in civil engineering application, also in architectural engineering applications. One of the most typical examples would be the I-shaped section. If you look at the I-shaped section, so I-shaped section consists of three different thin plates, isn't it, right? So combination of three different thin plates. So basically the individual plate can be modeled by plane stress condition, okay? This is one example, typical example found in real applications. Alright, and then this is the basic idea regarding principle of superposition. So when we have complicated load systems, we can decompose these complicated load systems into simple individual units. And then after getting solution for individual units, then we can superpose the response together to obtain the solution for the original problem. This is the principle of superposition. And then here are the learning objectives. As I told you, we have two different parts. The first part, we want to talk about the behavior pressurized vessels, where we use a concept of the plane stress. And then after that, we'd like to talk about a principle of superposition to handle the real problems. Alright, so before we talk about the pressurized vessels, I'd like to take 5 minutes break.